Yeah, so let's start.
Okay, thanks, Ted. Thanks, organizers, for having me here. Yes, I guess my talk is a part of entertainment program because it's not actually about string field theory. So it's about higher spin gravity. But I guess many people, including in this topic, we always had this feeling that we share a lot in common with string field theory. Topic even more in common than say with hardcore string theory. So would be nice to get to the bottom of that and actually find some explicit contact points. Isn't it too loud or no? It's fine. Yes. Okay. So, well, let me. I okay. I can't scroll. Yes, I cannot. So, but I can give the entire talk just based on the first slide, if you will. Okay. Yes, good. Since it's going to be long talk, 1 hour, so let me give first main messages because I'm going to review many topics, and for sure every next slide should come as a surprise for you, but sometimes it will come as a surprise for me as well. So the main message here is that there is this such idea of higher spin gravities, and the idea is to look for extensions of gravity with massless higher spin particles. I will explain why it may not be such a stupid idea to do that, but in few words, uh, the main idea is that massless fields are gauge fields. Gauge fields have some gauge symmetries. The more gauge symmetry, the better. In a sense, you have less counter terms, better chances to have quantum gravity model. But of course, there is no free lunch. And these theories are hard to construct, and there are some issues and so on, no goes that prevent you from doing this easy in few lines. In fact, this is one of the maybe topics that is special in having many more no-go results than yes-go. Uh, so there are many more ways not to actually construct higher spin gravity than to construct. So I'll review the basic idea, then I'll present a list of higher spin gravities available at the moment and also some closely related ideas. Within ADS-CFT correspondence, existence of higher spin gravities can easily be explained because they are duals of very simple conformal field theories called vector models or Chern-Simons vector models. And in fact, there was some excitement about these and still is related to recently discovered dualities in 3 dimensions among these theories. Somehow, all of these dualities can be guessed based on the fact that certain higher spin gravities should exist. And there is also a number of conjectural relations between higher spin gravities and string theory, which I'm going to review. And I think one thing for sure is that we also love strong homotopy algebras and things like that, homological perturbation theory. We use them a lot in this topic. So about some reading, because until recently there hasn't been any comprehensive review of the topic, but this year we published this Snow Mass paper, which I invite you to read. So it summarizes on few pages what has been achieved and also reviews some of the future prospects. And if you want some technicalities which actually don't cover this strong homotopy algebra business, I invite you to read also this year lectures by Dmitry Ponomarev. Okay, so this is short plan or rather keywords because I will be jumping from one topic to another. So these are more like keywords I would like to go through. First, just invitation to the topic, what's spin, what's special about spin, what's special about higher spins. Then I'll present some no-go, yes-go results, just exploring the power of higher spin symmetry. In particular, we'll see what that is. And then we try to understand the place of high spin gravities through ADS-CFT and where also all possible relations to string theory now reside. Then a list of high spin gravities available. Then I'll talk about the theme. Of course, I want to plug certain things that I personally involved in. So I'll talk about some specific model and its relation to three-dimensional bosonization duality. In particular, review what that is. And then there is an interesting part how just ignoring the existence of higher spin gravities to think about higher spin symmetries themselves. These are some infinite dimensional symmetries that extend conformal symmetry as a useful tool on the CFT side. And maybe a few random words about techniques that we use in this topic. Yes. Okay. So we know since Wigner that particles have two numbers assigned to them: mass, which is continuous, classical, and nothing special about it, and spin, which is really quantum, discrete, and so on. And the fact that is not well understood, I think, still is that physics, I mean, types of theories, physics you can describe with certain theories, they depend a lot on the spin content involved. So far we have only one fundamental particle with spin 0, that's Higgs, all right. All matter comes as spin half particles, and then there is a very special line here, because starting from spin 1, you can have gauge fields. And then, of course, quantum field theory is not about free fields, it's about how to construct interactions, and interactions depend a lot on the spins involved. So, for example, here we can try to play the following game. Take several spin 1 massless particles, several photons, and try to make them interact, try to introduce interactions. Then surprise, well, of course, under certain assumptions, you know, solution is just Young-Mills theory, and underlying structure is Lie algebra, but it was not put in the beginning. You discover this as a result of looking for consistent interactions. So as we can put it, so in principle, physicists could have easily discovered Lie algebras before mathematicians if we just look for consistent interactions of massless spin 1 particles. So then we can try, well, just increase spin by 1 unit, so massless spin 2, and play the same game. Have several non-interacting gravitons and look for interactions. Then, to some surprise, first of all, you can have that. So gravitons can have color. Well, again, of course, everything is done under certain assumptions, but gravitons can have color, and this is perhaps because there is only one graviton to determine space-time geometry, so there has to be one true graviton, so we can't have color here. And then again, the solution to that problem is given by Einstein-Hilbert action if it's constrained to be no more than 2 derivative. And then again, you discover Riemannian geometry and things like that that were not present in the free theory of massless spin 2. And if we just jump back by 1 unit and try to do something like this for spin 3 half, then we find no solution. But if we're clever enough to realize what the source of the problem is, then we need to extend 3 half with at least graviton and maybe some other fields, and then the resulting consistent theories are supergravities. And again, you find supergeometry and things like that. But starting from spin 2, there is another line, because it's quite easy to show that if you cross this line, then even before constructing anything, it's quite easy to show that as long as you have say massless particle with spin greater than 2, you have to have infinitely many of them. Just symmetry tells you that. Even before you construct any theory, you can see that the smallest multiplet that can possibly work has to have infinitely many of these particles. And if we make them massive, then of course we have string theory that is, well, you can view it as a vast extension of gravity with massive higher spin particles. And yes, okay, so we believe this to be a solution to the quantum gravity problem, which somehow indicates that higher spin states must be important for that problem. And yeah, so various examples, but of course this is not a rigorous statement, but the very existence of string theory, whose consistency relies on the presence of infinitely many of higher spin states in the spectrum. Also, we can check some of the lower spin theories along the supergravity lines, which are plugged by divergences, and well, for n equal 8 case is still open, but I think nobody actually believes it can be finite. And also, if we look through the SFT lenses, then any reasonable conformal field theory in dimension 3 or greater has single trace operators of arbitrarily high spin. So one way or another, from these ideas, you can come to conclusion that it may not be stupid to look for theories with higher spin fields, and in particular, quantization of gravity seem to require higher spin states. And then the idea of higher spin gravity is to look for the most minimalistic extension of gravity by massless, that is gauge, higher spin fields. So why gauge and why massless? Because in the UV regime, where you expect at least perturbatively most of the problems of quantum gravity are coming from, in the UV regime, everything should look massless. So why not to put this into the game to begin with? And then the idea is that since the massless fields are gauge fields of some sort, this gauge symmetry behind infinite multiplet should they eliminate counter terms, and you can get a quantum gravity model on least line. So basically, if you believe this folklore, then quantizing gravity through high spin gravity is almost about just constructing at least one example of classical theory of this sort, because the symmetry should be so huge that it will eliminate counter terms, so you don't actually have to compute any quantum corrections. Maybe that's an idea, but sounds a bit too easy, right? Okay, so we'll see what goes wrong along the way. And this is maybe the most technical slide I have. So if you have some minutes in the evening, you can try to solve the following problem. So you shouldn't be surprised that a massless spin-S particle can be described by a rank S tensor. So you just have a symmetric tensor with S indices, which is straightforward generalization of, say, Maxwell A mu or graviton G mu to arbitrary spin. And then there is, again, extension of gauge symmetry, which comes with rank S minus one gauge parameter and one derivative here. So which is straightforward extension of these formulas. So now, uh, uh, we can ask this question in any background, but of course people prefer maximally symmetric and especially flat. But the question I'm asking can be asked in any background. And yes, so the problem, yeah, that's why I have nabla here. So it doesn't have to be flat. So the problem is there are pretty normal second derivative actions for these fields known since 70s. And the problem is to look for interactions and maybe some corrections to gauge transformations as well, which are already present for Young-Mills and gravity type theories. And well, just find some action and see what happens. So that's the basic problem. Yes. And since many things, well, since behind this idea is some powerful infinite dimensional symmetry, it's well, even before looking for such theories, you can see what this symmetry tells you about basic observables. And the usual situation is that if your symmetry is too small, it's not very helpful. If it's too big, like say in many integrable theories, you can fix everything even without Lagrangian, Hamiltonian, or things like that. Symmetry tells you everything. So higher spin symmetry sort of combines features of the two, because almost everything is fixed and there are very few theories that actually can accommodate such a huge amount of symmetry. So let's just have a look from the symmetry perspective, what you would expect to find for the basic observables. For example, we are in flat space, but we soon jump to NTD sitter. So let us start in flat space. So then, of course, asymptotically, if you look at S matrix type observable, asymptotically, you just have linearized gauge symmetry, which is equivalent to not having, well, having the symmetry is equivalent to decoupling of longitudinal states. And then, as Weinberg showed many years ago, if you combine this symmetry with a low energy limit, then it gives you funny conservation law for your theory. So here you have momenta, four momenta of summed over all external supposed to be massive states. Mu are open indices, four-dimensional indices, and GI are coupling constants between these massive external states and this low energy massless particle you can have here. So when your massless particle has spin 1, this just gives you sum over GI, which in this situation we call electric charge, and this is just charge conservation. For S equal 2, you see there is a tension between these and the momentum, momentum conservation that is already there. So if you don't want to trivialize your scattering completely, you'd better make all of these coupling constants equal to each other, so that this thing factors out and you don't impose more constraints than just momentum conservation tells you. And this, as Weinberg says, is well, is some kind of equivalence principle that all matter couples universally. So now, if spin is greater than 2, well, you have many indices here, and then you can't just make it look like a product of of momentum conservation. So you really have a lot of constraints on your scattering, and then non-trivial S matrix can't survive. So basically you come to conclusion that if at least one massless higher spin particle is in the game, then S matrix has to be 1. And this, by the way, again, doesn't tell you anything about whether these theories exist or not. Just if you're in flat space or doing some collider type of experiment, you can't see massless particles in your S matrix. So maybe they confine or don't exist, or everything is possible. Yeah, okay. And this global picture, because I was talking about S matrix type observables, this global picture is in some tension with local picture. So globally, we expect S equal 1, But locally, and it's more or less a textbook statement, people showed many years ago that given any three helicities, lambda 1 to 3, there is at least a cubic interaction or amplitude that you can write, and it's consistent Lorentz invariant and so on. Moreover, as you can see from the formula, it doesn't even discriminate, well, a lower spin, higher spin, it's very homogeneous. Yes, please. No, not, yeah. Mhm. Yeah, this formula is four-dimensional, and many things I'll be talking about are four-dimensional, but the idea of higher spin gravity is general. There will be three-dimensional example as well. Okay, so this formula doesn't even discriminate lower and higher spin fields. So puzzle why we have all these seeds of interactions, but can have theories that actually apply those. But the possible resolution is that that's just life, or interactions in the actual series. These interactions conspire in such a way that the result in S matrix is 1, which is not too surprising, because if you have some infinite dimensional symmetry, you expect your theory to be integrable of some sort, which means, well, also means that you have too many conservation laws, so your S matrix has to be trivial of some sort. Not necessarily 1, but trivial of some sort. Yes, please. Yes, we will see. Yeah, it's absolutely, it's 3-point statement, and if we actually seriously look for such theories, we have to go further. Yes, please. Yeah, it's off.
Particles are massless.
Yes.
Okay. So this is an amplitude or a vertex, because on shell, a vertex only exists when the particles are collinear.
Yes. Okay. So of course, so it's well, in this notation, it's of course spin or helicity, so it's amplitude and it's continued to complex momenta. But there is an off-shell vertex that corresponds to that. You can write. But you're totally right. So I mean, if you're looking at physical scattering, then of course for spinning fields, for spinning massless fields, amplitude 3-point amplitude vanishes, right? So you either think of this as a seed, well, at the off-shell level, or using some of the amplitude techniques where you need to continue to complex momenta, you can, this has to be just starting point. Okay, so this is just some tension in the sense that there are some seeds at the cubic level, but at higher level, like globally, in terms of S matrix, we don't seem to have any interesting scattering going on. So let's jump to anti-de Sitter space, which is another nice maximally symmetric background. And now we have some good control through also ADS-CFT correspondence. So the standard ADS-CFT lore tells you that as long as you have gauge field in the bulk, in anti-de Sitter space, the dual operator has to be a conserved tensor. For example, if you have spin 1 here, the conserved tensor is actually current, is a conserved current. If you have spin 2, that is graviton, the conserved tensor is stress tensor. And okay, just analytic extension of this rule gives you that for spin S, the dual operator is a rank S conserved tensor. And now we can think, well, how many conformal field theories we are aware of where you can have higher spin conserved tensors. So it's very easy to construct such things in free conformal field theories. You can take free scalar, free fermion, free super and Mills, and then just by writing phi, many derivatives phi, you can arrange things in such a way that the tensor is conserved. And then in free CFTs, you can find actually infinitely many conserved tensors. So for every spin, there is a conserved tensor. But actually, the opposite statement is also true. So if you have a conformal field theory in dimension 3 or greater with a stress tensor and at least one higher spin current, then you can show that in fact there are infinitely many of these currents, and the correlation functions of those look like in one of the free CFTs. So that's some nice result that basically tells you that this is a complete picture. And again, so we seem to have very good control over holographic S matrix, because as long as you have a theory in anti-de Sitter space with massless higher spin fields and your boundary conditions don't break these symmetries, so dual operators are conserved tensors, the holographic S matrix has to be given by correlation functions in some of the free CFTs. And as these people put it, it's also kind of extension of Weinberg and Conlon-Mandel type theorems to ADS-CFT. So higher spin symmetry in ADS-CFT implies, unless it's broken, that holographic S matrix is given by free CFT. Okay, but there is an interesting twist because in ADS-CFT correspondence, we have a right to impose different boundary conditions, Neumann-Dirichlet boundary conditions. Moreover, on every field, we can impose different boundary conditions. And if you impose another boundary condition on just scalar field from the higher spin multiplet, then higher spin symmetry will be broken in a very special way to which I will come later. So it was even called slightly broken higher spin symmetry because it's not generic violation of symmetry, so that currents are not conserved, but they're not conserved in a very special way. And then the result in conformal field theory that accommodates that is a large N critical vector model, also known Wilson-Fisher. So this is exactly Phi to the fourth textbook theory, but at the critical point where it becomes a conformal field theory. And this is nice because this theory actually describes part of the physics, but in condensed matter sense. So then with this boundary condition, holographic S matrix for high spin gravity is given by a large N Ising model. And there is extension of this scenario to so-called Chern-Simons meta theories, which is also related to three-dimensional Bosonization duality. I'll come to that later. So there is some new interesting twist that in these theories, there is still some remnant of this infinite dimensional higher spin symmetry. And there is another idea that again within ADS-CFT correspondence, that you can in fact forget about ADS theory. You can take any CFT you like and try to rewrite these correlation functions as holographic correlation functions of some theory in anti-de Sitter. So you can try to reconstruct your theory just from correlation function if you like it. And as a warming up example, you can take free CFT. So your higher spin currents are some bilinear operators like phi, DDD, phi. So which means that computing 3, 4-point correlation functions and so on are just a bunch of weak contractions, so everyone can do that. You can write the most general ansatz for cubic interaction and the bulk and arrange free coefficients in such a way that you get exactly what you want. Then you can jump to the next level where you glue two of the already obtained cubic vertices into exchange diagrams, sum them up. Now, there's a calculation that you can do in the back of the envelope with these weak contractions and basic ADS-CFT dictionary that tells you that the sum over exchanges gives you exactly the structure, exactly the 4-point function, but with coefficient 2. And the correct correlation function with a wrong coefficient is a wrong correlation function. So, which tells you that you have to arrange your quartic interaction in such a way that it subtracts 1 from here, which also tells you that the quartic interaction has to be non-local. So it has to be given by the sum of the exchanges. So your quartic interaction is non-local of this type. And then the question is what you can do in such a theory, because it looks a bit non-local. And there are, in fact, interesting ideas that, well, how to phrase it, that you can see that if you look at Veneziano amplitude, it's just one amplitude. There is one diagram. You don't sum over exchanges. So therefore, Veneziano amplitude has poles in S and T channel easily. So it has to have that because it has to accommodate everything. So here we have kind of similar situation that you sum over these exchanges, but well, every diagram on CFT side that corresponds to that has to have poles in two channels simultaneously. So it looks a bit, we're trying to apply field theory rules to something that doesn't want to be field theory. It likes to follow more stringy pattern, and there are few papers that try to elaborate on that. Yes. Yeah, me too, actually. So yeah, I didn't make any comments about the bottom of the slides because I couldn't see them. No, I'm joking. Yes.
So it is clear that it is not local, but you could think, couldn't you think that there is it has been obtained by integrating out a massive field which doesn't reach really the boundary?
Yes, amazing idea. So in some scenarios, people could even find, but in a different, not in ADS-CFT, it was a different theory. But so far, uh, the, well, it hasn't come to the state where it looks nice. But yes, that would be actually a natural idea that if you have some non-localities, probably it's because you integrated out certain things. Yes, I agree. Okay, but in principle, within ADS CFT, you don't expect every CFT to give you interesting quantum gravity theory in anti-de Sitter space that can be treated by, well, as semi-classical. There are some constraints on CFT you have to impose to achieve that, because generic CFTs, like, I don't know, Ising model or just super and Mills at generic coupling, they don't correspond to anything nice, local, and so on. And apparently vector models, including just free conformal field theories, they don't satisfy some of these assumptions. So this kind of behavior you would expect on general grounds. And now the question is what to do with that. And now let me try to summarize all of these restrictions that we have on S metrics. So far, there hasn't been anything said about actual theories. It's just the power of higher spin symmetry imposed on observables at infinity. So this formula alone, if you are in flat background, implies that S matrix has to be 1. And I put some star, star, star here because I will get this 1, but in an interesting way from something that is not 1. Well, if your boundary conditions preserve all of this higher spin symmetry, then correlation functions have to be given by free conformal field theories. And an interesting scenario is that if you play a bit with boundary conditions and so on, then S matrix has to be given by Chern-Simons meta theories, where, well, which first of all describe some physics, but secondly, they also feature some nice recently discovered dualities, which I will talk later. Yes, and now let me come to relations to string theory and just to remind you what I said about ADS-CFT scenarios. So massless higher spin fields are dual to conserved tensors on CFT side. And if you take some free theory, say free superionomills, then these higher spin tensors look like phi, many derivatives phi. And even though computing correlation functions is very easy, you just do weak contractions, the fact that connected correlation functions don't vanish implies that you have to have some non-trivial cubic and so on interaction in the bulk to explain that. So no, just free. No, it's super. I mean, it has all the symmetries you want, but just it's not an interesting CFT maybe because it's just a bunch of free scalars, free fermions, and free spin 1. But I mean, you have a coupling constant, you can set it to 0. Yes, exactly. Yeah. So it's, but you'll see that people actually wrote quite a few papers about that. So the point here is that even if you're looking for gravity duals of free conformal field theories, they are highly interacting because still correlation functions don't vanish. Something in the bulk has to explain that. And now let me come to the most basic ADS-CFT scenario where you have strings on ADS5 S5 versus superenamils. So this is a diagram in the coupling constant space of superenamils theory. So you can choose 1 over n and 't Hooft coupling. And then when n is large, we have this planar limit. Well, of course, strictly speaking, planar limit is just one line here. So it's of measure 0, but it's very important scientifically because you have integrability and can actually compute observables all the way from weak to strong coupling. So then when 't Hooft coupling is small, you have classical limit, so you can trust your Feynman diagrams and so on. And whenever coupling is 0, exactly on this line, you have your free Young-Mills, super Young-Mills. Okay, but in general, in the middle of this, we have no tools to tame this theory. So now let's have a look at the string side. In string theory, we have 3 dimensional parameters, which is what is radius of anti-de Sitter space, typical size of the string, and also Planck length. And again, we can arrange them into 2 dimensionless things. And then if Planck length is the smallest possible, but also string length is much smaller than ADS radius, then basically we have point-like strings where all massive modes are frozen, and the good approximation, which takes into account only massless modes, is supergravity. So now we can still take Planck length to be the smallest, but try to increase typical size of the string. So then, as long as we do that, well, the size of the string even becomes greater than the radius of anti-de Sitter space, and at the end you have very long string that dwindle over anti-de Sitter space. So it's hard to say what's going on. This limit is highly counterintuitive, and well, it's even hard to argue that you should have any meaningful field theory type description in ADS for this limit. However, if you jump back to CFT side, then well, it's clear that you just have weakly coupled superennuis, or in the limiting case, just free superennuis. And then you have your higher spin currents, you have your higher spin symmetry, and so on. And that was basically the first occurrence of the idea of higher spin gravity in IDS-CFT, which is due to Sandberg. But then many people like Klebanov, Polikov, Sezgin, Sandel, and many others, they found simplest scenarios where instead of taking conformal field theory with matter in matrix representations of gauge symmetry, you take vector models. They have much less operators and are easier to deal with. So yes, good. So therefore, there are several ideas where you can see higher spin gravity on one side and something coming from strings or related to strings on another. So the most basic conjecture is that free superennuis should be dual to some higher spin gravity plus a lot of matter. And I put question mark because the actual, I don't know, Lagrangian or whatever of this theory is not known. So it's a hypothetical conjecture of a conjecture. In a sense. Okay, but recently it has been made much more precise on the string side. So I draw attention to these recent papers by Gabardine and Gopakumar, who came up with a proposal for what tensionless string should be in order to be dual to free superennuis. And there is a much more elaborated story in ADS3 background by the same and other people. There's also, a few papers on fishnet. I don't know if you know what's that, but that's some strange limit of superennuis, which again has weakly coupled regime where you have higher spin currents. So the most simple conjectures along these lines are not with superennuis, but with vector models, where you have this free scale or fermion or interacting versions called Wilson, Fisher, and Grosvenor, and more general Chern-Simons meta theories. And here one can go all the way to ABJ, which are again some Chern-Simons theories, which are known or conjectured to be dual to type 2A strings on ADS4 CP3. So there is some relation along these lines going on in ADS4. And okay, there's as a consequence of that, there's another relation with a theory that I'm working on. I will talk later about that. So now, given that quantizing gravity, higher spin gravity is almost equivalent to constructing classical theory, and we've seen there are some abstractions to doing that in one line. So it's interesting to see who survived actually. So who we have in okay, that's an old slide, but it didn't change. Yes, yeah, I think I fixed this. Okay, so in 3 dimensions, in 3 dimensions, there are plenty of theories and which people worked on. And the idea is as follows. So we know that in 3 dimensions, Einstein-Hilbert action with cosmological constant can be rewritten as Chern-Simons theory for SL2 plus SL2. So if you take a bigger Lie algebra, and almost every Lie algebra is bigger than SL2 here, and you make sure that under certain embedding of SL2 into that, you have higher rank representations, higher than a joint, then you'll see fields with many Lorentz indices, which you can interpret as higher spin fields. And again, at the free level, you can see familiar formulas that you can match with higher dimensions. So that's one idea. And similarly, you can do things with extensions, with higher spin extensions of conformal gravity in 3 dimensions, because again, it's known to be of Chern-Simons type. And yeah, one can also introduce partially massless fields and so on. So then another theory or class of theories which exist in even dimensions are called conformal higher spin gravities. So in 4 dimension, this is extension of wild gravity. So it's not an extension of Einstein-Hilbert action, it's extension of conformal gravity. And there is a simple way to understand why this thing plus dot dot dot, I mean, can exist. is to take your, well, if you take some conformal matter in 4D and couple it, say, to stress tensor to conformal metric, evaluate effective action. Usually there is some anomaly piece, there is log divergent piece, whose coefficient is exactly wild gravity action if we ignore topological Euler characteristics. So from which you can, well, understand that if you have free conformal matter in 4 dimensions, then you have higher spin currents. You can couple them to sources which generalize conformal metric to higher spins, evaluate effective action. There has to be some local piece in front of log, and this is dot 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 here. Yes, yes. So it's not yes. Okay, it's not Einstein Hilbert plus yeah. Okay, then there's theory that I will review in a second called chiral. So you see that in all of these theories, they avoid no-goes one way or another. For example, in 3D, you just don't have any propagating fields. So 4D conformal, okay, it's non-unitary high derivative to begin with, and chiral, I will explain how it avoids it. So then there are some other nice ideas which are not exactly about local field theory, but still they are nice to be mentioned. So first of all, one can continue this reconstruction, namely take your favorite correlation functions and try to rewrite them as a theory in anti-de Sitter space. So, well, you can just follow brute force. So there is a clever idea called collective dipole, where you take full partition function on CFT side and massage it by doing some change of variable in such a way that it start looking like a path integral over fields that you would like to interpret as living in anti-de Sitter space. Let's put it like this. It may be a bit long, but okay, the idea is clever. But then, of course, you get something non-local, but it gives correlation functions that you started with by definition. Then there's different idea based on IKKT matrix models, but where you take, well, as the underlying structure, one of the higher spin algebras. Of course, it's non-commutative field theory. And then there is one of the oldest idea, which dates back to Vasiliev. Let me phrase it in a modern language, where actually all these strong homotopy techniques come into the game. So the idea is to find some super manifold equipped with homological vector field Q, so that you have your L infinity algebra, and write a KZ type sigma model like that. So now the subtlety here is that in order for these equations, which are known to describe many topological field theories, but in order for these equations to describe non-topological field theories, Q manifold has to be infinite dimensional. And then the problem is that if you perform some change of coordinates on this Q manifold from the field theory point of view, it will generally look like a horribly non-local field redefinition. So the open question here is how to adjust this Q so that it actually corresponds to some nice field theory. And there's just one example again. I'm working on this exactly where it was achieved and recently, very recently. Okay. So now let me plug in my own research, which is about the thing that we call chiral higher spin gravity. And in order to understand this higher spin extension, it's better to start with some textbook thing, which is self-dual Yang-Mills. So imagine just Yang-Mills theory, F mu trace, and try to impose light congauge there. It's just very useful to explain what's going on at the level of physical degrees of freedom, because light congauge eliminates everything in physical. So as a result, out of A mu, two components will be gone. So you have just two scalars representing helicity +1 and -1 states, and the entire theory will be formulated just in terms of these guys. So then you have a normal kinetic term. Then your cubic vertex splits into plus plus minus and minus minus plus. And you also have quartic interaction. So if you erase these red terms, what you get is known as self-dual Yang-Mills. And the properties of self-dual Yang-Mills are as follows. First of all, tree-level amplitude vanish. One-loop amplitudes do not vanish, but coincide with, say, all helicity plus amplitudes of QCD, which is nice. But more general comment is that, which you can do the same thing for gravity versus self-dual gravity, is that self-dual theories are consistent truncations. So even though this action looks well, very non-unitary because you're just missing the complex conjugate piece and the quartic. Even though these theories look like very non-unitary, everything you compute in them is unitary in the sense that it's a part of unitary observable of this bigger theory, of which this one is a truncation. And then there are some fruitful ideas how to well, understand full Yang-Mills theory as a perturbation of self-dual one, and there's story related to integrability, instantons, and twistors. So what we constructed is more or less a higher spin extension of self-dual Yang-Mills and gravity together, and it's a theory that contains fields of all spins, and we can try to play exactly the same game I played on the first slide. So we can take massless spin as particle together with some textbook self-interaction, and we can ask if there is some completion of that is local, Lorentz invariant, and so on. And then as a result, we'll find, well, we will be forced by consistency to introduce particles of all spins, including 0 and 2, so scalar and graviton are necessarily part of this multiplet. And then all these interactions will enter your theory with a funny dependence on the helicity. There's gamma function sum of the helicities. And this is the smallest higher spin extension you can construct. Now, very similarly to self-dual theories, you can compute all amplitudes, tree-level amplitudes, they all vanish. Then interactions are naively non-renormalizable because the number of derivatives is basically sum of the helicities. In particular, you still have this 3 graviton vertex with 2 derivatives, and the higher the spin, the more derivatives you can have. So interactions one by one are naively non-renormalizable. But if you compute one loop amplitude, then there are no UV divergences, and effect is more or less like in n equal 4 super Mills, where the theory is renormalizable to begin with, but it takes you some supersymmetry to prove that certain momenta get factored out. So instead of log divergence, you have something finite. So here we have the same miracle, but infinitely many times. And if you do the calculation, then one loop amplitude is as follows. So it has all helicity plus amplitude of QCD at one loop, then some higher spin dressing factor, then this funny sum over 1, which is like effective number of degrees of freedom. So it's 1 plus 1 plus 1 plus 1, but it's a pure number. It's not related to UV divergency. And then there are many results in the literature that deal with vacuum one-loop corrections to higher spin gravities. And these results actually instruct you to set this sum to 1, which you can do with the help of zeta function. But maybe for now, it's not important. But yes?
A curiosity. Infrared divergences are there. First of all,
yeah, I think we just ignore them. So as an all massless series, yes.
And you are in 2,2 Minkowski. The signature is 2,2.
Well, okay. So of course the integral you do in Euclidean signature, but the amplitude.
Yes, self-dual Yang-Mills is 2,2.
No, self-dual Yang-Mills can be just a complex theory in Minkowski signature, or real in Euclidean, or 2,2.
Because there is the old story of the so-called n equal 2 superstrings.
Yes.
Which have a dual self-dual spectrum.
Yes, yes.
But they are defined in 2,2. Well, if you don't want to mix up with complex fields, you have to go in 2,2.
Yes, I agree with you. So I think actually all signatures make sense, in the sense that in Euclidean you can be talking about instantons, 2,2 makes things real. But if you treat, say, a self-dual Yang-Mills or this theory as just complex theory in 4 dimensions, it's also useful because, as I said, in these theories, all amplitude you compute are actually amplitude, say, in self-dual Yang-Mills gives you amplitude of QCD. So yes, the action is horribly non-local, but it gives you something nice that, yeah, that's the idea here. Yes, okay. So one comment about this factor is that any field theory with infinitely many fields is not quite a field theory. So sooner or later, you will have to give a recipe how to sum over the spectrum. So this the occurrence of this sum is not higher spin feature, it's just would be a feature of any theory with infinitely many fields sooner or later. Yes, please. If question is short, I can just repeat it.
These at the higher even at one loop, are these planar amplitudes? So
yes.
Okay, so this is planar.
Yeah.
I will also ask a question. Sorry.
Yes, you're allowed.
So, but your coupling constant is dimensionful or not?
Okay, good. So the coupling constant you hear, yes, it has to be dimension full, and we even call it L Planck in the sense that graviton is in the game, but I don't pretend it's a fundamental theory of nature. But yes, the coupling constant is dimensionful.
So then wouldn't you expect divergences, non-unitarity at large momenta, just like whenever you have dimensional quantity, you know, have G.
Yes, yes, there is this
unitary in that sense.
Yes, there is this argument that, well, we all know, we teach QFT course, that if you have coupling constants of negative mass dimension, that you expect in trouble. So here the miracles that you expect in them, but if you do calculation, they don't happen, because this argument is just well, it's like with the UV divergences in general. There might be divergence, but if you compute it, maybe it's not there. So yeah, so here Yes, good. Well, okay, so let me just go quickly through the features. So first of all, I call them stringy because they reminiscent of string theory. And in fact, there is some conjecture how this thing can be related to string theory. So the spectrum is necessarily infinite. Also, you can try to introduce Yang-Mills gauges. In a sense, you can make spin 1 nanobillion and other fields charged under that. But the calculation shows that you can do this only in Chen pattern way. So you have UN or USPN. You can't introduce, I don't know, E8 chiral higher spin gravity. It doesn't work. So only a la Chen pattern. Yes, we have to deal with these spin sums, which in string theory will take care of. But here, what saves the day is that the spectrum we have is rather small, so simple tricks with zeta function seem to work. Well, action contains parts of Yang-Mills in gravity, and as you see, higher spin fields soften amplitudes, but in this case, they soften them to death. So in the sense that the amplitude becomes trivial. So if you regularize this number to 0, then at the beginning, you have this Sol plus QCD amplitude. But if you want to be consistent with Weinberg, and there are some results that tell you that you should regularize this to 0, then the final amplitude vanishes. So you do get S equal 1 from something that was not 1. So we are consistent with Weinberg. Well, but we can also go to another space-time because well, like de Sitter or anti-de Sitter. And now the effect we have, the positive effect we have, is that absence of UV divergences in flat space should guarantee the same in curved one. But now in anti-de Sitter space, we don't actually have trivial holographic S matrix. So this chiral theory is not dual to something 3. I will explain what it is dual to in few. Yeah, that's just to show some specific formulas. I'm not sure if it's useful, but let me. Yes. Keep it on.
Yeah, like a question. Did anything interesting happen with higher spin gravity in the Sitter space?
Well, yes, I'll make comment about that. Yes, it's already on the slide. So just to give you an idea of, say, how action look like. So for this theory, we have action in the light cone gauge, equations everywhere. Well, light cone gauge in flat space, equations everywhere. But there are some truncations of this theory of which you can think of higher spin extension of self-dual Yang-Mills and self-dual gravity. And for these guys, covariant actions look very simple, but you have to start not with the actions we used to, like for spin 1, it's in terms of F menu and so on. You have to take action that people in self-dual Yang-Mills look like very much. So you have some 0 form, which plays the role of self-dual part of F menu for spin 1 and self-dual part of wild tensor for spin 2. And for spin 1, this is just your gauge connection. For spin 2, it's self-dual part of spin connection. So the main fields are these ones. And in fact, you can easily introduce Yang-Mills type and gravitational interactions. And for example, you can pack all these fields into one generating function. And if you take Poisson bracket as your kind of nanobillion structure here, This, by the way, gives you the same algebra as W1 plus infinity. Then if you take this curvature in place of this linearized one, you get a consistent theory. But I don't know, maybe it doesn't click with anyone. So let me come to Chern-Simons meta theories and bosonization duality, because somehow higher spin gravities, just the very idea of these theories, played an important role in discovering three-dimensional bosonization duality. And I will be dealing with conformal field theories in 3 dimensions. So we can take scalars or interacting scalars, fermions or interacting fermions, all of them in vector representation of some global symmetry. Then we can gauge this global symmetry, and luxury we have in 3 dimensions, we can add Chern-Simons term here. As a result, we get 4, well, in the simplest case, there is a zoo of these Chern-Simons theories with various matter multiplets and supersymmetry. But in the simplest case, we have this, say, 4 pure theories, which start from free boson or with Ising or from fermion or from Gross-Neveu. And the red ones are based on fermionic matter, blue ones are based on bosonic matter. So these theories describe some physics. They break parity in general because of Chern-Simons, and they have 2 parameters, the number of fields n, and this kind of 't Hooft coupling n over k. K is Chern-Simons level, and of course in the large n limit I'll be dealing with, lambda is almost a continuous parameter. And now what 3-dimensional bosonization duality is. So you can put these 4 theories at the corner like this, and then you can ask the question, okay, I have this almost continuous family, 1 parameter family of theories, parameterized by this 't Hooft coupling constant lambda, but what is this family? And the conjecture is that, say, if you start from Ising model and you have this 1 parameter family, and you start from fermion, then it's the same 1 parameter family. But you see, Wilson-Fisher is formulated in terms of bosonic matter, and free fermion, obviously, in terms of fermionic matter. The conjecture is that, in fact, these theories are the same as conformal field theories. So all correlation functions, anomalous dimensions, they have to be the same, and likewise here. That's the basic conjecture of 3-dimensional bosonization duality. Yeah, I hope it's clear why it's called like that, because it's in 3 dimensions, and this is some non-trivial relation between theories involving scalars in fermions. And well, if you take three theories, obviously we have higher spin currents. And in general, in these theories, phi or psi are not nice gauge invariant operators to deal with. The simplest gauge invariant operators are exactly these higher spin tensors, which are conserved in the large n of free limit. But if you depart from these limits, you can see that they are not conserved. Of course, because there is a general theorem that if you have conserved high spin current, then it has to be free CFT. So they're not conserved, but they're not conserved in a very special way, because you're in CFT, so everything is an operator. If you have non-conservation law, then the guy that is on the right that determines your non-conservation has to be an operator again. And if it's generic operator, then your symmetry is just broken. Probably there is nothing useful we can say. But in this case, operator is a composite operator built from the currents themselves. So in a sense that higher spin currents violate their own conservation. And this is a useful idea. So one can use this non-conservation together, well, with some assumptions on how this operator look like to actually fix correlation functions.
By the way,
yes,
the way you write is suggesting something like a Youngian or something like this.
It's not Youngian. I will tell you what it is. Yes, good. And first of all, you can ask, well, I gave you this chiral higher spin gravity. It's some nice local field theory to which you can apply usual rules of field theory, and it exists in flat and anti-de Sitter space. But being theory in anti-de Sitter space, you can ask what it is dual to. And it cannot be dual to this Chern-Simons meta theories because interactions are chiral. So it can only be dual to subsector. But the first useful consequence of this is that the very existence of this theory tells you that in Chern-Simons meta theories, there are closed subsectors of correlation functions that don't talk to each other. And of course, it's hard to find these subsectors at the level of action because the basic fields are not even gauge invariant. Also, we could show that these chiral theories are very rigid, so there are no free parameters. You can't just throw in one, you can't just add one additional field into the specter or remove spin 13. So they are very rigid theories, and therefore, well, at least at the level of 3-point functions, chiral and anti-chiral interactions, they cover the entire space of possible interactions. So you can ask, how correlation, 3-point correlation functions in Chern-Simons meta theories should look like. And this amounts to the question of how to glue chiral and anti-chiral pieces together. These are like two bricks that there is nothing you can do with bricks themselves, but you can glue them, you can put them together in a way that is parameterized by one additional parameter, and this gives you all 3-point functions in these theories, which is also consistent with Maldacen and Zhiboyedov findings. And then bosonization this way is manifest because bulk fields, bulk higher spin fields, they're dual to higher spin currents, and they're completely insensitive. They're blind to whether these currents are built from scalars or fermions. So if you can fix your correlation functions just from, say, higher spin symmetry, then you attempt to prove the duality because it doesn't matter in which theory you compute them. There's a unique answer for that. And now I come to your suggestion whether it's Yangian or not, because I want to tell you how one can put higher spin symmetry as it is to use on CFT side, because it is also an infinite dimensional extension of conformal symmetry. So let me start first with free theories. Let's take free CFT, for example, free scalar. So we can construct these higher spin conserved tensors, and then stress tensor is just particular member of this infinite multiplet. And we know that stress tensor is something responsible for the conformal algebra charges. So you can ask what these other higher spin conserved tensors are responsible for. And in fact, it gives you some infinite dimensional algebra. It's a Lie algebra by construction because the commutator of two symmetries is a symmetry. But if you start from free scalar or free fermion, because equations are linear, you can easily see that not only the commutator of two symmetries is a symmetry, but the product of two symmetries is a symmetry. So as a result, what you get is some associative algebra that contains conformal algebra as a Lie algebra, but also infinitely many generators. And you can formulate it in this way, like any free CFT gives you some associative algebra, and we call it higher spin algebra. So, but the usual logic is that as long as you have something conserved, you construct charges form the algebra, but also all your operators, they live in some representation of this algebra. And the miracle that is necessary for the three-dimensional bosonization duality is that higher spin algebra that you construct from free boson and free fermion are actually the same. Just as infinite dimensional algebras containing conformal algebra, they turned out to be the same. Now you can try to see whether you can compute correlation functions as invariants. Of course, correlation functions are invariant under conformal symmetry, but it's not very useful, so to say, because it doesn't fix completely these correlators. But on these infinite dimensional algebras, there is a trace. You can think of these algebras as some infinite dimensional matrix algebras. So there is a trace, and you can actually compute correlation functions as invariants that, well, that tells you that they're not only conformally, but higher spin invariant. And in fact, there is some relation to string field theory at the technical level, because these guys that you plug in to compute invariants, they're projectors. And projectors play important role in many solutions of string field theory. So, and the star product here is actually the Weyl star product. So, and there is nice algebraic story behind having projectors in the star product algebra. Okay, one way or another, you can compute correlators as invariants of higher spin symmetry. And so now what happens in these Chern-Simons vector models where symmetry is not there because currents cannot be conserved? But since, as I already told you, they are not conserved in a very special way, so that you have some composite operator constructed from currents themselves, maybe you can put it to practical use. That was an idea first explored by Maldacen and Zhiboyedov and dubbed a slightly broken higher spin symmetry. Also, another interesting fact is that higher spin currents, just as a multiplet of operators, form an irreducible representation of this infinite dimensional higher spin algebra. And again, this action gets deformed whenever you depart from free or large n limit. Now the question, what is the right mass? So the right mass is not Yangian, but the right mass is L infinity. because you can so you can just look at these formulas and see, well, if you can formulate it as a kind of algebraic relations. And yes, you can, in a sense that you can start from simple L-infinity algebra that just has a bracket, which represents bracket in the higher spin algebra. And it also represents the fact, delta xi of j, that higher spin currents form an irreducible representation of this algebra. This gives you L-infinity algebra on higher spin algebra and module of this algebra. And then you can ask, well, if there is a consistent deformation of that would accommodate these kind of terms, and the only consistent structure you can think of is L-infinity algebra. So you need an L-infinity that extends a given Lie algebra with some module of it. And okay, this can be constructed, and for this particular algebra, you can also show that this nice invariance that you have at the free level, they admit certain deformation. This deformation is unique. So from purely algebraic perspective, you can show that, well, that since correlation functions are completely fixed by the symmetry, it sort of proves three-dimensional Bosonization duality in the sense that whatever microscopical realization of theory you have, correlation functions have to coincide. And maybe, yes, there was many questions. I think I'm almost out of time, so let me just give one last slide or two. So I've been talking about massless higher spin fields, and saw them well, as very special creatures that don't like actually to interact, and there are many problems with them. But string theory spectrum is full of massive higher spins, and in fact there are no goals about massive higher spins. So it looks like no challenge in the sense that at least from the higher spin community perspective, there are very few papers on massive higher spin fields, but it's not because there is no challenge, it's because the challenge is much higher. The problem with the massive higher spin fields is that you have, well, if you just consider them at the free level, you want Klein-Gordon equation, but you also want them to be transverse. And this transverse is an additional constraint. So obviously these equations are not Lagrangian. And then you can ask, well, how I can even get them from an action? And you need lots of auxiliary fields which come in a strange pattern, or say from canonical perspective, you have theory with second class constraints. So the point being is that it's very hard to make sure that effective actions you're writing, they actually propagate the right number of degrees of freedom, because you need to make sure that something like this survives at the nonlinear level. And success stories here are known only for low spins. Like for S equal 1, we know that massive spin 1 fields can easily be obtained from spontaneously broken Young-Mills. For spin 3.5, in fact, as far as I know, there is nothing in the literature. And spin 2, well, you can extract spin 2 from massive gravity or by gravity. So that's a consistent theory that allows you to find some nonlinear deformations of these equations. And what we proposed recently, just to start talking about massive higher spin fields, is that, well, if you are in 4 dimensions, as we usually live in, then instead of this kind of symmetric tensors, which correspond to SS type representation of SL2C, you can take a chiral type description, which deals with 2S, 0 representation. So at the technical level, the nice feature here is this representation is irreducible once you decompose it down to the Wigner little group. So this field already has the right number of degrees of freedom. So basically everything you write is a consistent interaction. And that was the problem here, because apart from almost measure 0 terms, everything nonlinear you write here will be inconsistent. So here everything you write is consistent, but maybe imposing parity at the full level is a bit tricky, and yeah, there are some consistency check of that. And now I have some random comments with the hope that maybe some of this will click with you, but it's not something that I covered in the main part. So there was a question about what's with de Sitter. So again, so you can try to think of higher spin gravities in de Sitter, and then they actually, you can see that they require some high derivative corrections even in the gravity sector. And there are some interesting papers that are related to cosmology and so on. So if one day we see necessity for high derivative corrections in some cosmological backgrounds, it doesn't mean that it has to be described by higher spin gravity, but higher spin gravity gives you specific numbers for what these high derivative corrections have to be. Then there are many more quantum checks in various high spin gravities and holographic high spin gravities where you don't have any meaningful action, but you can still compute things sometime without it. Then, as I tried to argue, this non-locality problem in holographic high spin gravities somehow tells you in a sense that these theories want to be closer to string theory and Veneziano type amplitude, because whenever you compute this amplitude, they feature poles in different channels. That's exactly the property of Veneziano and exactly not the property of field theory. Yes, for those who like higher structures, so higher spin algebras in general can be understood as deformation quantization of some coadjoint orbits, and Moyle-Weil is just a specific case. And somehow this has eddy CFT built in because these coadjoint orbits correspond to unitary irreducible representations of some pre-conformal fields. Then various types of projectors in the higher spin algebra, say Moyle-Weil algebra, they play important role, and say from holographic perspective, it's the projector property that implies the weak theorem on CFT side. Then these equations of this type give you lots of examples of L-infinity structures that in fact originate from A-infinity via symmetrization map. And there are also, well, we also use sometimes homological perturbation theory to construct those. And from deformation quantization point of view, you should be able to quantize some Poisson orbifolds instead of manifolds. There are many formal exact solutions of these equations known, which also rely on existence of projectors. And if you want to classify things in these theories, you come to the question of how to compute certain Chevalier-Lebesgue cyclic and Hochschild cohomology of these algebras. So these are just random comments. I hope at least some of them clicked with you. And let me summarize. So I hope I explained that some high spin gravities do exist just as local field theories, while some of them are non-local and to be understood better. And probably we have to go beyond field theory. And this is where actually we can make contact maybe with string field theory techniques. So for example, the spiral high spin gravity is just normal local field theory, passes some quantum checks, and in a sense, high spin symmetry turns out even more to be more or as powerful as supersymmetry. And there's nice relations to Chern-Simons meta theories and Bosonization reality. So there are many CFT pairs with local or non-local high spin gravities on one side and string theory on another side. And there are also, just on the high spin gravity side, certain string features of amplitudes that you can notice. Well, high spin symmetry can be interesting on its own as a physical symmetry of this three-dimensional conformal field series. And I think this is the first occurrence of L-infinity as the actual physical symmetry. So in a sense, it does act on physical operators rather than encode, say, the gauge structure of your theory within, say, BV formulas. Yes, we like A-infinity, L-infinity, and other things. And yes, I actually think I was just idea yesterday that at some point we should have a kind of round table with some people from higher spins and string field theory trying to find the exact points of contact because where the wall is sort of the lowest, and we can jump and make specific statements about the relation between the two. So thank you very much. May the higher spin force be with you, whatever that is. Thank you for your attention.
Okay, thank you for your talk. Are there any questions?
So when you talk about the self-dual Yang-Mills theory, and you show this one loop amplitude dressing, so for the all plus amplitudes, this is a rational function.
Yes.
Right, that one where everything is kind of jumped by.
Mm-hmm.
So was it important there somehow or not?
Well, in fact, my good friend and co-author, he showed that there is some relation between the chiral theory and self-dual Yang-Mills in flat space. in the light cone gauge. So eventually, I believe that many of the nice features I talk about, they can be explained, say, from this self-dual perspective, or maybe there is and some people are working on that, there is a nice twister formulation, and in twisters, it's very natural to formulate self-dual series. So there is some nice twister formulation like Chern-Simons. That's the recent proposal by a student. There is a Chern-Simons section in twister space, and it explains most of the features that we have hard time to dig out, and just did calculations that in few years will be shown to be relevant because you can show everything in one line. Yes, so that's.
And just one question about when you turned into the massive amplitudes, because the massive amplitudes are not just fixed by the Lorentz symmetry and the little groups. So is it that thing also complicates the story somehow, or was it important for you for the massless case that these 3-point amplitudes were fixed, or
Well, so could you please explain this relation between massive and massless?
No, that in the massless case, if you just fix external helicities of the states for 3-point amplitudes, it completely fixes the kinematic structure.
Yes.
Right. And this is not true for the massive case.
Yes.
Yeah. So if that part somehow complicates the story for you, or
for massive, you mean?
Yeah, for the massive. Or was it somehow important, this rigidity of the 3-point amplitudes for the massless case to make it work?
Well, so both things. So in the sense that yes, for massive fields, we first of all we know that these things exist as effective field theories, and one thing I didn't talk about is application to black hole scattering. This is why we are doing this. So we want effective theory that describes scattering of black holes. Yes. So for given massive spin S, there are infinitely many of interactions. Well, maybe at the cubic level, still finitely many, but more than one that you can write. And but I think at the technical level, for massive fields, the problem is that it's hard to control this extra constraint of transversality at the Lagrangian level. And so we found some way to achieve that in 4 dimensions, but then parity is not manifest. While for chiral theory, well, I wouldn't say that the fact that kinematics is fixed play any role, but just calculationally it simplifies things. But also for given 3 spins, there are several amplitudes. It's for given helicities, there is a unique, and then in between we have to sum over all spins propagating in exchanges or loops. So what played the role is the specific dependence of coupling constant on helicities, this 1 over gamma functions that I showed. This actually that you can call like the higher spin miracle, because only this dependence of coupling constant on helicities glues things together in a local Lorentz invariant way. And eventually, yes, it is responsible for all these nice effects like cancellation of UV divergences and so on.
So concerning the UV finiteness of this chiral theory, now the leading divergences in flat space and curved space are the same. So
I hope so, yes.
Yeah, there should be, but the subleading not necessarily. So did you check whether these were absent?
Yes, that's a good point, and we would love to do that, but unfortunately we don't have an action. So we have an action in the light cone gauge, which lies in flat space, but in ADS it's not yet available, and actually we don't do light cone. We don't want to do light cone gauge. Okay, nobody wants, but at least in flat space it was useful. So we don't have an action in anti-de Sitter to actually do this calculation, but we hope to be able sooner or later.
Yeah. So the question about that in this chiral higher spin theory, you presented the S being trivial nevertheless.
Yes.
So just as a general message, so how do you manage to get something non-trivial even though you have to satisfy that? Or maybe I didn't understand how you eventually managed to have S equal to 1.
Well, so it was okay.
And also, do you have to? Is it a general lesson that you either have to sacrifice locality or unitarity, or you can get away with it eventually anyway?
Yeah, okay. So remember, so at least at one loop, there was pretty normal non-vanishing factor related to helicity plus and QCD, but there was this sum over degrees of freedom, 1 plus 1 plus 1, which basically counts the number of degrees of freedom. That's a factor or similar one that would be present in any field theory with infinitely many fields. So these are not quite field theories in the sense that you have to give certain prescription of how you would like to sum over the spectrum. Say, if you have infinite spectrum because of some kind of Kaluza-Klein reduction, then your regularization should have something to do with Lorentz invariance in dimension high. So we don't have that. So, but there are many results in the literature where similar or more complicated sums over spins occurred, and there were non-trivial tests showing that the zeta function regularization is the right one to be applied, and in this case, it just gives you 0. So it was kind of non-trivial amplitude times something that you have prescribed value for anyway, because there are infinitely many fields, and it's not thanks to us, but to many other papers which indicate that you should actually set it to 0, which is also consistent with Weinberg. So we got 0 amplitude from something non-zero. Yeah.
Maybe very naive question. Do you have in your theories maybe some remnants of non-perturbative dualities like S duality?
That's a really good question. I'm not aware of any conjectures towards that, but maybe, yeah, okay, one can think, and just nobody asked this question before. Yeah, so maybe there is a simple sort of conjectural duality along these lines, but nothing in the literature, I think.
Yeah, so you mentioned this fact that in this higher spin algebra, you naturally find these Champatton structures like that somehow suggests a sort of a sort of relation with open string theories.
Yes.
But on physical grounds, since you have gravity in these higher spin theories, I would perhaps also expect a relation with closed strings field theory, maybe some tensionless limit of closed string field theory. So is there some research in this direction? Has someone ever thought about this?
Well, I think one of these hypothetical dualities which go through ABJ model and so on, it's with open type 2A strings on edges for CP3. But yes, that's a good question. No, I don't know how to explain graviton, sort of the presence of so maybe it was a massive spin too, but in the tensionless limit it got something massless. So I don't know.
I mean, in the open string you get a graviton because you go to the tensionless limit.
Yes.
In closed string you already have a graviton somehow, right? So, it would sound like a very natural setting.
So maybe it's a feature of the tensionless limit itself. Yes.
What he said that has confused me a little, because the action you wrote was with light cone, okay, higher spin with chain patterns. So you have spin 2 with colors.
Not quite. So you have spin 2 living in the product of fundamental anti-fundamental of UN. It contains 1. It contains trivial representation, and that's the actual graviton. So you have
yes, but you have also a spin 2 with colors.
Yes, you also have spin 2 with color. But if you confused why is it possible, there is only one strict result I know on that. It's by Damour, Boulanger, Arnaud, this no multicolor graviton theorem, and of course they make a lot of they have enough assumptions to exclude higher spin scenario.
So you are saying essentially that you have a massless spin 2 with colors.
Yes, we have massless spin 2. One of them is graviton, other with colors. Yes.
Okay, well, it's graviton. Are you sure it is graviton? Because I mean,
well, it has gravitational interaction with.
It has a gravitational interaction with the others.
Yes,
okay.
Yes. But the point I explained is that it actually evades any of the no-goes that are.
No, it was not about the.
Okay.
I was more puzzled about the fact that you have the color, the part with colors.
Yes, yes. So there are massless spin 2 with colors and without. Yeah.
maybe I can ask one more question. I saw it on some of your slides. Was partially massless something.
Yeah. Yes.
Yeah.
Okay.
Is it this accidental symmetry which appears on DS or anti-DS and removes 1 degree of freedom?
Well, so that was about 3 dimensions. So in 3 dimensions, we actually showed that everything with, which is topological, is Chern-Simons. So it sounds a bit stupid, but if you start from, say, higher spin action, it's not. So everything in 3 dimensions is topological and Chern-Simons. But extrapolating from higher dimensions, you know that there can be so-called partially massless fields in the presence of cosmological constant. And they can also be described in Chern-Simons way. But I would say they have less gauge symmetries than massless fields, but more than massive. Massive have none. And partially massless, they're sort of in between in the sense of amount of gauge symmetries. But the only example we know of consistent partially massless with higher spins is in 3 dimensions, which is Chern-Simons anyway.
Because I know this story from the point of view when you have massive gravity and then on de Sitter background, for example, you have some accidental symmetry on this particular background, which removes 1 degree of freedom.
Yes, that's exactly the thing.
But for me, the problem was all this, that it's kind of the symmetry which appears only at this particular background, and as soon as you perturb it a bit, it disappears. So isn't it a problem?
Okay, so first of all, we have opposite starting points. So you take massive gravity, right? And then you tune mass to be what it has to be in terms of units of the cosmological constant, then you have accidental symmetry. But we start from something that is massless or partially massless on a fixed ADS background, and then we try to introduce interactions while taking care of the symmetries we already have. So that's exactly the consistency. So we don't want to lose or gain any of the additional symmetries. And what we show is that, yes, there is a deformation. And in fact, if you write everything down, it's still a Chern-Simons section. And then you can say, well, can I extend this in which sense I can extend it from de Sitter or anti-de Sitter? Well, if you turn on other fields that are present in this theory, because it never comes with just one field, you have, say, graviton, bunch of these partially massless specific spectral fields. So if you have these non-trivial backgrounds, which you should not maybe call gravitational because there are other fields activated, then everything is okay with gauge symmetry, so you can preserve it. But if you ask, well, can I put partially massless field on generic gravitational background? I think the answer is no. Yeah.
Are there examples of higher spins of 2D gravity?
Sorry?
Are there examples of higher spin versions of 2D gravity? Maybe.
That's a good point. So in fact, people are working on this right now, like over the first year, a few last years. So you can, you can formulate JT gravity as BF theory. And if you take, in that case, BF is, I guess, SL2. So if you take something bigger than SL2, then it has higher spin interpretation. So there are few papers on that. Yes. So in 2D, one can extend, look for higher spin extensions of the Jackiw-Teitelbaum gravity. Yeah.
So if I can ask, so in one of the last slides on the comments, you said that the higher spin symmetry can constrain the R cube term.
Yes.
And I wonder whether it differentiates whether R squared or R cubed.
Well, it depends how we parameterize. So what I was having in mind is that, so at the level of cubic amplitudes, if we are in 4 dimensions, we can have 2 independent. One is Einstein-Hilbert, and another one that is like +2, +2, +2 in complex conjugate, which you can extract from Riemann tensor cube. Of course, there is a mixture between, but you can extract. So this is what I meant here, that there are 2 independent vertices of graviton in 4 dimensions. One is the usual one, 2 derivative, and another is 6 derivative. And higher spin gravity has specific coefficient between the 2. But of course, it also requires a lot of fields. So it's not like you can easily decouple them and present it as a like low energy theory.
Gives you a concrete prediction for the R cube term?
Yeah. There's a specific ratio between coefficients of, in fact.
And is it in agreement with string theory?
You tell me. So actually, the coefficient is sort of easy to find because There was this section I showed. It had Planck lengths to some power, but that's dimensional thing. You can treat it for alpha prime. And there was 1 over gamma sum of the helicity. So the coefficient here is 1 over 5 factorial. The coefficient here is 1. Okay, so the relative is 5 factorial, 120, up to this Planck length or alpha prime. Yeah.
Okay, so I think one should check because this is known correction in string theory.
Yeah, but I can bet right now it won't coincide.
It won't coincide?
Yeah, because it doesn't have to. In a sense, well, it's even in our best dreams, this is some part of the tensionless limit, because I mean these theories, they have very few fields, like just one species of one spin basically up to color. String theory has much more, so it's a vast truncation of, say, tensionless limit of string theory. So in this sense, I'm not sure to which extent. Yeah, as we discussed, it's not even clear to which extent the graviton we have is the graviton of string theory, because it may be just massive spin 2 of open strings in the tensionless limit becoming massless spin 2. So yeah, I would not even know before any of these conjectures made more precise what to take in string theory. Well, usually people do, but again, since many of these things are at the level of conjectures, you don't actually know what is the specific string state that is mapped to this. But maybe it can be worked out.
Maybe we can wrap it up now because it's after 12:30 and we can get lunch. Okay.
Amazing.
Okay. So let's thank Zhenya again.
Yes, thank you. So it's a program talk in exchange of food.